Okay, we are into chapter 8, which is on atmosphere and ocean interactions. So, not um atmosphere land or land ocean. So, the focus is specifically on atmosphere ocean interactions, which usually tend to be the biggest part of the climate models, even though obviously you need land and, of course, glaciers and other things. The main idea is to orient ourselves as to how models represent some of the key processes. So we talked about equator to pole temperature gradients, having to move energy from surplus regions to deficit regions, and why that gives us the kind of zonally averaged meridional circulations we have talked about. But this animation from this site called climatereanalyzer.org offers a nice animation of the sea surface temperature and precipitation from ERA interim reanalysis product, and you can see the kind of key features of the energy budget when you open up the zonal mean into global maps. So sun moves north and south, so you expect that to have serious impact, significant impact on energy balance and manifest itself in, of course, winds, rainfall, and first temperatures, humidity, and so on. So this shows you very clearly the north-south migration of the warm waters in the deep tropics. So you can see the warm waters here moving north during the boreal summer months, and then cooling a little bit and coming south during the boreal winter months when the sun is in the south. And there is obviously very strong zonal contrast because the trade winds and the fact that the ocean has boundaries as opposed to the atmosphere, which has no boundaries. You end up with the strong zonal contrast with divergence, upwelling, and cooling in the eastern oceans here in the Pacific and Atlantic, but the Indian Ocean is different because it has the monsoonal circulation. The high latitudes get cold during the winter months, especially over places like Greenland where there are a lot of glaciers, and Antarctica where there is, of course, massive glacier, and the Arctic as well. So you can see some sharp fronts. You can see the differences in the structures over the Indian Ocean, which is pretty warm throughout the year, versus other oceans in the tropics where the temperatures can get cold during the strong upwelling season, and you have these subpolar subtropical fronts in the sea surface temperatures and so on. And while the distribution is obviously closely related to the radiation balance, but you can also see the ocean-atmosphere interactions, which themselves depend on the structure of the ocean, the land mass, the boundaries, and so on, makes for big differences locally. So in a model, in a coupled model, we don't have to worry about those kinds of details. If you give it the land configuration and the top of the atmosphere energy coming in, it should be able to do most of these things, and as we talked before, they do, and there are slight biases and errors because of various uncertainties. Then that wind and ocean atmosphere interactions have to produce the scales of rain. So you have the narrow bands here, the subtropical gyres, the mid-latitude storm tracks, and so on, and the split ITCZ. We talked about the intertropical convergence zone, which you can see in the winter month is to the south, but as sun moves to the north, the monsoon creates a very unique structure here with strong ITCZ on the ocean, but also rain over the Indian Ocean and the Bay of Bengal and so on and so forth, which is dramatically different than what happens elsewhere. Okay, so there are many scale selections involved in time and space, where evaporation happens, where precipitation happens, and so on. So when you want to understand atmosphere-ocean interactions and how to represent them in models, you have to understand what is happening at the interface. Obviously, there is energy exchange, momentum exchange, and exchange of matter, like greenhouse gases or the nitrogen, oxygen, and also salts, and so on and so forth. And the exchanges, for example, of heat happens through what we will see soon as heat fluxes. So the question then is, do the models directly compute heat fluxes, or do we need a formula for the heat flux, and then what are the uncertainties that come with it? So those are the kind of details we will look at. But that directly brings us to thinking about coupling of physical model components. So now we are getting really into climate modeling. So this is nice diagram from NASA. I think David Herring created those. So you can see that we had sun's energy coming in. We had energy balance happening. Some of the energy penetrating the ocean, which we didn't talk much about in our energy balance so far because it's kind of a detail. So then the equator to pole temperature gradient is set up, circulation is set up, rainfall in the tropics, and mid-latitude storm tracks, and there is exchanges between the atmosphere and the ocean, energy and momentum going into the ocean, ocean currents getting set up, and all kinds of time scales being created with ocean currents, and places where water comes up, what we call upwelling, and places where waters converge and go down, places where waters get heavier and sink, and so on and so forth. Those are all physical coupling processes, but as you can imagine, the vegetation on land and in the ocean have serious impact on greenhouse gas budgets, which affects radiation balance and hence would affect climate as well. So the basic idea of the energy balance and equator to pole temperature gradient is straightforward, but once you begin to add other components like the biogeochemical components, things get much more complicated. Then you have to worry about phytoplankton, the so-called biological pump, which takes down carbon dioxide and carbon that is photosynthesized. You have organic carbon, inorganic carbon, nutrients being circulated, but effectively affecting the air-sea interaction also through aerosols like sea salt, sea spray that's putting aerosols, sea salts into the atmosphere, which act as cloud condensation nuclei and affect clouds, cloud formations, evaporation, water vapor, which is of course part of the physical coupling as well. And you have carbon dioxide exchange. So if ocean takes up a significant fraction of the carbon dioxide, then it's a big part of the energy balance as well. So the physical biogeochemical coupling and then land ice coupling and so on also begin to affect the climate. So air-sea interactions in that sense obviously begin to affect the climate itself as well. So we have to worry about all those things. So in the coupling the physical model components, which is what we will focus on, air-sea interactions in this chapter, we have to think about momentum transfer and heat transfer and energy transfer through evaporation, because evaporation is stripping the energy from the ocean by breaking the hydrogen bonds between water molecules, and that energy condenses in the atmosphere, or water vapor condenses in the atmosphere and releases that energy, which is a large part of the driving mechanism for global weather and climate. Okay, so this is kind of setting up the background. We'll come back and look at specifics of how heat exchange happens and how they are not directly always measurable. You can measure temperature, winds, humidity, radiation, and so on, infrared and shortwave, but to convert temperature, humidity, and winds to fluxes, we need certain formula which have certain parameters. So there is parameterization involved. So in the actual climate models, the ocean and atmosphere are exchanging energy, but the atmosphere typically computes basic variables like temperature, winds, humidity, and we have to convert that into fluxes. We have to give it to the ocean, then does with it, and then gives it back to the atmosphere. My computer went blinking for a minute, but anyway, so those are the kinds of things we will look at in the next podcast. Okay.